In this video, we're going to take a small break from explicitly talking about electricity to talking about some of the math behind what we're seeing when we do Gauss's law. Gauss's law, if the symmetry allows, is the easiest way to evaluate the electric field. But a lot of the math, I think, because we don't explicitly perform a lot of the integration involved, looks like sorcery. We just kind of wave our hands at it and go, oh, and of course we know this answer. Well, that's a little unsatisfactory. So let's actually see what's going on. One thing we see in Gauss's law is a lot of some dA. Well, what in the world is dA? Okay, it's a differential area element. Great, what the heck does that mean? Well, let's back up a step and ask what it is when we evaluate some sort of dx. Well, what am I doing when I integrate dx? Well, you might say, well, you're just getting x. Yeah, but what am I doing? Remember, the integral is an actual s. It's an s for summation. I'm summing up a continuous quantity. In this instance, a continuous length. And so let's say that I have a bar or a rod or a wire sitting here, and I've got one end sitting at 0 and the other end sitting at L. And you want to know the length of the bar. You might say, well, this is trivial. The length is L. You can tell from the coordinates. And yes, you can, and it is trivial. But let's see what happens when I apply the calculus here. And it's really not a big deal. I'm going to separate this bar into little bitty delta x's. I'm assuming we're using the x direction. And then I'm going to let those elements shrink down to a dx and integrate to add them up. And so I get integral dx from 0 to L. Remember, these are all definite integrals because I'm actually adding up a physical quantity. So they have to be definite integrals. Integral of dx, of course, is just x evaluated from 0 to L. Fair enough. 0 at the lower limit, I get L. And you might go, well, this is a lot of work to get something that I already knew. What is this, the new math or something? And you're right. We would never actually do this to get this length. But sometimes we have to do this if we are multiplying this dx by some sort of function. Even if we're not, I think it's helpful to keep this in the back of your mind to remember what it is we're actually doing when we integrate. We are actually adding up a continuous quantity. Okay, fair enough. Let's look at something a little bit more complicated. What if I have some sort of rectangle, and again, let's put it in a coordinate system. We'll say that this is my origin, and in the x direction, this goes to some distance L, but in the y direction, this goes to some distance M. And I want to know what the area of this thing is. And again, you might say, well, you just multiply this side by this side, and you're right. But let's look at it, how we do it with the calculus, because it's going to be instructive. I want to divide this up into a lot of little delta A's, right? Delta A for every one of these things. These are all delta A's. And you can probably see where I'm going. I'm going to let this shrink down to a differential, but let's ask ourselves what delta A is. Well, just like I had some delta X here, you can imagine I can divide my y-axis into little bitty delta Y's. And so every delta A can be expressed as some delta X, some delta Y, right? These are lengths. They're displacements if you want to think about it like that, but they're really lengths. They have units of meters, and so when I multiply them together, I get units of meters squared, which means this is an area. Okay, well, let all of these shrink down to differentials. I get on the right-hand side dx dy. This is still a differential length. It still has a unit of area unit of meters with each of these differentials. Put them together, I get meters squared, which means on the right-hand side, I have let this shrink down to some dA. This is behind what's going on with a dA. Anytime there is a dA, it's a differential area element, but what's happened is I've taken the differential length in one dimension and multiplied it by a differential length in another dimension, and that's gotten me my dA. In Cartesian, this is really easy to see. It's just dx dy. It's a little bit more complicated in spherical and cylindrical, which we'll see in a second. Well, we'll see spherical in a second. But this is what's happening in the background. I mean, let's just keep it going. That's a terrible looking rectangular prism, but maybe we can get the idea. I now have little d V's. I'm not going to draw any more lines because it's going to get really convoluted. I've got some dv. Okay, well, I'm going to have another axis now. I'm going to have a z-axis. Let's say that runs from 0 to n. All right, it's going to be hard to draw here, but let's say that this runs to some n. So same thing, divide each of my axes into little differential lengths, or first deltas, delta x, delta y. I should do this. Delta v is equal to delta x, delta y. Now delta z. And then let all of these shrink down to a differential. So I get dv is equal to dx, dy, dz. And of course I would when I integrated this, I would let it run to my limits. Now, you might ask, okay, well, how in the world do I integrate this? And that, whether or not you ask that question depends on whether or not you've been through Cal 3 or not. If you're in my class, it's a 50-50 chance or so that you've been through Cal 3. This is actually a triple integral, which we don't always write the 3 integral signs when we talk about triple integrals, but that's what it is. This would be, a double integral, because I've got 2 differentials. Now, if you haven't done this before, that looks really scary. Let me assure you that it's really not. This is the same thing. Let me rewrite it down here. The triple integral of dx, dy, dz, I can rewrite as integral dx times integral dy times integral dz. So the triple integral here is just really 3 integrals. What makes it maybe a little more complicated is if I have functions in here. But in this case, I don't. We'll see one with the function in just a few minutes. But in this case, it's just dx, dy, dz. And if I put in the appropriate limits, I'm going to get, after I do the integral, I'm going to get some length times some width times some height, which I know as my volume formula. Again, much more work than it would take to actually just figure out the volume of this thing. But that's the machinery behind all of this stuff. There are certain situations which we need to do the calculus. So this is the machinery behind what's happening. Trivial and Cartesian. But let's look at something that is not so trivial and definitely not Cartesian. Let's move to spherical coordinates. I might need to get a volume element in spherical coordinates. I see this when I have to determine the amount of charge inside some Gaussian sphere, especially if the charge distribution is a function, not a constant, right? So here's 1/8 of a sphere. I don't want to put the whole sphere up here because it's going to get really convoluted. I don't own these graphics, I should say. I just took them off the internet, but they're really nice. So I've shown you 1/8 of the sphere, but imagine that the whole thing's here. Here's my volume element. Just like in Cartesian, here's my little delta V. This is going to be my delta V, but I'm going to let it shrink down to a dV. And so the first thing I would say, what took me by surprise when I was learning how to do this, was I'm just going to find each individual side of this box-looking thing and multiply them together to get the volume. And when I first saw that, I said, well, that's how can you do that? It's not an actual rectangular prism. They've got curved sides. And that is true, but remember, we're letting these things shrink down and shrink down to differentials. So as these curved sides approach 0, they actually become straight sides in the limit. And so in the limit, it's okay to just figure out what each of the 3 sides is, and then multiply them together. So my dV, if I'm trying to determine what my differential volume element here, which will tell me how to integrate this, is just going to be one side times another side times another side. They've shown you the answers here, but we're going to go through how they get them. First of all, there's an XYZ coordinate system here. We are doing this in spherical coordinates, but it's easier to define angles if we put our familiar Cartesian in the background. First angle to see is we've got theta here. Theta is sometimes called the polar angle. It's measured down from the polar axis. In this case, they've called it z. So theta is going to be measured from the z-axis down, and they've shown it to you right here. The other angle is called the azimuthal angle. Here is listed as phi. This is going to lie in the xy plane, and we're just going to rotate around here. I will say, unfortunately, depending on what textbook you're using or what class you're in, sometimes you will find phi used here for the polar, theta used here for the azimuth. I remember when I was taking Cal 3 and Physics 2 at the same time. In Physics 2, they used this convention. In my Cal 3 class, they used phi here and theta here, and it just about drove me nuts. But it's okay. So you will see these angles labeled differently sometimes. Most physics departments and textbooks I've seen use this convention, so we'll stick with this. All right. With that said, let's see if we can determine the sides of our box. This one I think is the easiest one, and they've shown you the answer. It's dr. But if you imagine that I'm coming out from the center to some ultimate radius, I move through some delta r, and then another delta r, and then another delta r, and delta r, and delta r, and then delta r here. Now, let that shrink down to a differential, and delta r becomes dr. So that's one side of my box. One side of my box is just dr. So there's one side. I need the other two. Let's look at this side here. Now, if I look at it, this is at some radius r from the center, and I know that r is going to change, but if I'm looking at this particular box, it doesn't bother me that r is going to change for other boxes. That's what the calculus is for. But this is some radius r times some angle d theta, right? This from here down, moving down from the z-axis, this is some delta theta. Let it shrink down. I get some d theta. So I've got the radius r times delta theta. That's just an arc length, which is what this is going to be. In the limit, it's going to become a straight line. But this is some r d theta. Here's r. Here's d theta. So that's this side. That's my other side. Now, my third side, I think, is probably the most complicated one. That's this back side here. They've given it to you down here. What we're going to do is recognize that this sphere consists, I can draw it as a series of concentric circles, kind of moving down from the pole, right? If I can get that to actually show up. And there's my axis. And so if I'm starting here at the origin, I measure some theta here, and then there's a circle located at that theta. Notice as I move around that circle, theta is constant along this circle. Same with this circle. This would be a theta of of pi. Move around, theta is constant. And then there's another circle here. Again, if I move around, theta is a constant. So it seems like a good way to get this side of the box is to figure out what the actual radius of this circle is. This is not the radius of that circle, right? The radius of that circle is here. But it might be good if I'm going to treat this one like an arc length like I did the one on the side. If I can find the radius of that circle and then move around some d phi, that's going to tell me the arc length here, which again will become a straight line in the limit. Well, the trick comes to your rescue here. If this is theta, this line is just r. Again, this is my radius, r, from the center to this volume element. R sine theta gives me this length here, which turns out to be the radius of my circle right there. So r sine theta is this length times d phi gives me the arc length here, and that's the third side of my box, r sine theta d phi. All right, if you need to pause this video and go back and watch that again, I would recommend it. This is not the easiest thing to grab hold of. But once we have that, let me clean this up. I've got two r's, so that's going to give me an r squared. I've got a sine theta, and then everything else is a differential. dr, d theta, d phi, which I can rewrite, of course, as r squared dr sine theta d theta d phi. All I did was I grouped functional dependence, right? I've got an r squared and a dr. I'm going to group that together. Sine theta d theta, group that together. D phi, there's no function with that. So if I'm going to integrate this, in other words, if I'm going to integrate the left-hand side to get the volume, I'm going to have to integrate the right-hand side. But now it's obvious to see that this is going to be a triple integral over r theta and phi. Let's talk about limits. R is probably the easiest one. I'm going to go from 0 to some overall radius r. So I'm trying to find the volume of a sphere with some radius. We'll call it capital R. I'm going to integrate this expression from 0 to r. Let's come back to this one. D phi might be easy to see. I'm going all the way around the circle, right? Even as I did it over here talking about these concentric circles, I was moving all the way around the circle. That is moving through an angle of 2 pi in the phi direction. So this runs from 0 to 2 pi. And you might think, well, okay, theta is going to run from 0 to 2 pi too, because that's what, spheres do and circles do. But notice, as I moved around each of these circles, I came down some angle theta and I moved around. Came down some angle theta and I moved around. I came down some other angle theta and I moved around. If I continue to do that, right, if I get a theta here and a theta here, no big deal. But as soon as I go to a theta here, well, look, I've already counted that circle. If I can get my pen to work. I've already counted that circle. I counted it here. So if I move past the z-axis on the bottom, I start to count circles that I've already counted. This is what's called overcounting or double counting. So to avoid that, since my phi is moving around, I'm only going to let theta move from the top of the z-axis here to the bottom. So theta actually only runs from 0 to pi. And that's to avoid overcounting. Again, stop the video, go back and watch that and think about it if you need to. But now that I have this, I can actually run these integrals. This one's easy. Integral of r squared is r cubed over 3. That's going to be evaluated from 0 to capital R. Integral of sine theta, I'll write it like this, is the minus cosine theta. And that's going to be evaluated from 0 to pi. Integral d phi, this is the easiest one. It just gets you phi evaluated from 0 to 2 pi. Okay? It looks like I'm going to get, well, let's keep it like this for just a second. Let me go ahead and evaluate the outside ones. I'm going to get capital R cubed over 3. And then I'll do this, but in a second. But let's see what we get here. I'm going to get minus cosine of pi minus, now this minus comes from the fact that I'm subtracting the lower limit, but my function itself is minus cosine. So I get another minus cosine of 0, right? This is the minus cosine upper limit minus cosine lower limit. And then this just gives me 2 pi. All right, well, cosine of pi is -1. I'll write this first. Cosine of pi is -1. Minus -1 gives me 1. And then the two minuses become a positive. Cosine of 0 is just 1. 2 pi, 1 plus 1 is 2, times 2 is 4 pi. Lo and behold, I get 4 pi r cubed over 3, normally written as 4/3 pi r cubed. And if you were go to look up the volume of a sphere, this is what you would find. This is where that comes from, right? It's not an easy way to get this formula like there was with the Cartesian versions without calculus. So this actually turns out to be an important process. Now, one thing I want to point out from what are called the angular integrals here. The angular integrals are the ones involving the angles, d theta and d phi. In other words, everything except the radius. If I just bracket this off, I've already kind of bracketed, but let me use a Sharpie. If I just bracket this off, what do I get out of that? Well, notice I'll bracket it here. I get 4 pi. The r cubed over 3 comes from the radial integrals. The angular integrals give me 4 pi. Why is that important? Well, if you're in my class, this is just physics 2. This is not advanced electricity and magnetism. In this class, every function you're going to see inserted into this will involve an r. We do not, in this class, we don't let anything in our geometry depend on theta and phi. It all depends on r. In the next video, there'll be an example problem where you see what I mean explicitly. But if you know that, as long as you know that, and as long as you can do this in the background, you can easily evaluate these angular integrals without actually doing the integration. If you see this, sine theta d theta from 0 to pi, d phi from 0 to 2 pi, you just memorize, you know what, that gets me 4 pi. The angular integrals always contribute 4 pi, unless there is another function in here. Like if I had some sort of theta squared d theta, well then that's not going to give me 4 pi. But as long as I just have sine theta d theta from 0 to pi and d phi from 0 to 2 pi, that's going to give me 4 pi. It's a handy shortcut to have. But in general, you should be able to go through this. We'll see an example of when we might need that in the next video.